Welcome to The Explainer. Today, we're diving headfirst into what is arguably the most intense, high-stakes scientific hunt of our entire generation. We're looking at the completely transformative, slightly elusive, and deeply fascinating physics of finding a superconductor that actually operates at everyday temperatures. Just imagine a piece of technology that could completely rewire the global energy grid, revolutionize medical imaging, and change transportation forever. It's basically the holy grail of material science, and the race to figure it out is nothing short of an epic quest. So, right off the bat, you're probably wondering, the ultimate, unsolved question hanging over this whole field: is it actually possible to make a material that superconducts at room temperature and normal atmospheric pressure? Well, the staggering answer from experts is yes. According to physicists, there are absolutely no physical laws that explicitly rule out the existence of a material like this. The physics totally allows for it. We just have to figure out how to find it or, how to build it.
Here's our roadmap for today's explainer. 1. The superconductor dream. 2. Chasing higher temperatures. 3. Breakthroughs and controversies. 4. Theories and mechanisms. And 5. A new scientific roadmap.
Let's kick things off with Section 1, the superconductor dream. First, let's just ground ourselves in the basic science. A room-temperature superconductor is defined as a hypothetical material capable of displaying superconductivity above 0 degrees Celsius. That's 273 Kelvin or 32 degrees Fahrenheit, all while sitting right out in the open at standard atmospheric pressure. And when we say superconductivity, we mean that electrical current can flow through the material with literally zero resistance. None. It doesn't lose a single drop of energy as heat.
And why does this matter to you and me? Well, we actually use superconductors right now in incredibly advanced stuff, like the massive magnets inside the CERN Large Hadron Collider and those life-saving MRI machines at your local hospital. But here's the catch. These applications are massively bottlenecked right now because they require extreme, super expensive cooling, often using liquid helium just to work. An ambient temperature superconductor would instantly eliminate that bottleneck and trigger a full-blown industrial revolution. We're talking absolutely lossless energy transmission across our entire power grid and hyper-advanced magnetic levitation technology. It's a total game changer.
Okay, moving right along to Section 2, chasing higher temperatures. If we trace the history of verified, corroborated discoveries, we see this agonizingly slow, decades-long climb. For over 30 years, a mercury-based copper oxide ceramic called Hg1233 held the ambient pressure record at 133 Kelvin. That was set way back in 1993. Then, scientists realized something crazy. They could force superconductivity at much higher temperatures if they just applied immense physical pressure. In 2015, they took a hydrogen sulfide compound and literally squeezed it between two microscopic diamonds in what's called a diamond anvil cell. They achieved superconductivity at 203 Kelvin. And then, in 2019, scientists reached an incredible 250 Kelvin using highly pressurized lanthanum dicahydride. Now, 250 Kelvin, which translates to roughly minus 23 degrees Celsius or minus 10 degrees Fahrenheit, is absolutely huge. That is currently the highest accepted transition temperature on record. To put that into perspective, that's astonishingly close to the freezing point of water. But remember the catch here. This milestone was only achieved by crushing that lanthanum dicahydride under unimaginable physical stress. Just how much stress are we talking about? Well, consider the staggering conditions needed in recent experiments. Researchers recently took that older mercury-based material, the Hg1223, and squeezed it at 300,000 times normal atmospheric pressure just to enhance its properties, which I think it's safe to say makes building a standard everyday power cable out of it slightly difficult. But this extreme pressure research did lead to a wildly fascinating breakthrough trick known as pressure quenching. Researchers over at the University of Houston and Argonne National Laboratory squeezed that Hg1223 material inside a diamond anvil cell. But then, they removed the pressure incredibly fast. This sudden release basically tricked the material, locking it in a way that let it temporarily maintain its superconducting state. It actually sat at 151 Kelvin for up to 2 weeks without any crushing force applied to it at all.
Which brings us to Section 3, breakthroughs and controversies.
Welcome to the Wild West era of physics. Because there is so much pressure to find a breakthrough, we've seen some pretty wild claims lately. If we look at the current factual standing of these famous materials, the divide is super clear. You've got lanthanum decahydride sitting solidly in the corroborated camp. Everyone agrees it works. But then you have explosive claims like LK99, which supposedly hit a 400 Kelvin transition at standard room pressure, but it remains completely uncorroborated. And then there's carbonaceous sulfur hydride, which claimed superconductivity at 288 Kelvin under extreme pressure. That one, completely retracted.
Let's actually look a little closer at that last one, because it sparked a real crisis. You see, the scientific community relies entirely on strict, rigorous peer review. Recently, highly publicized claims of near room temperature superconductivity in a carbonaceous sulfur hydride and later a lutetium hydride by a team led by Rongo P. Diaz had to be formally retracted. Independent experts went in, reviewed the work, and identified massive flaws in the statistical methods. Ultimately, they found the data had actually been fabricated. It's a stark, frankly sobering reminder that in science, extraordinary claims absolutely require extraordinary, reproducible evidence. And we saw that exact same need for rigorous replication with the whole LK99 phenomenon. I'm sure you remember this from 2023. A Korean team claimed they had an ambient pressure superconductor operating up to 400 Kelvin, and the internet completely shattered. It went globally viral overnight. It felt like we just stepped into a sci-fi movie. But as major labs around the world furiously rushed to replicate the experiment, they uncovered the truth. The material actually had a higher electrical resistivity than standard copper. The perceived superconducting effects, like the magnetic levitation everyone was sharing videos of, were simply the result of impurities and ferromagnetism inside the material. It wasn't true superconductivity at all. Because of this chaotic, Wild West environment, leading experts are drawing a line in the sand. They're advocating for a massive shift away from the old Edisonian approach. That's the old-school method of relying heavily on trial and error, human intuition, and physically guessing which materials might work. Instead, they're pushing for a modern, programmatic approach. This means systematic investigation, heavy computational design, and constant bidirectional feedback loops between the theorists running the math and the experimentalists in the lab. We need this to prevent false positives moving forward. Let's dive into the core physics with Section 4, Theories and Mechanisms. So how do we actually find the real deal? Researchers are mapping out some incredibly complex theoretical pathways. Take British physicist Neil Ashcroft, for instance. He theorized that solid metallic hydrogen, which you'd have to create at a mind-bending 500 gigapascals of pressure, should be a room-temperature superconductor. And that's because of its high speed of sound and super strong acoustic vibrations, a process known as phonon-mediated pairing. Other teams are looking into exciton-mediated pairing using organic polymers. And right now, massive computing power is being thrown at ternary superhydrides. These are highly complex structures like, wait for it, dilithium magnesium hexadecahydride. Try saying that 5 times fast. But computer models actually predict that specific material could achieve superconductivity at temperatures soaring all the way to 473 Kelvin. Finally, let's look at the future in Section 5, a new scientific roadmap. To keep this massive search on track, researchers from UC Davis and other leading institutions recently laid out a roadmap, and they drew a brilliant parallel to the early tech industry. They compared our current superconductors to the early days of electronics, back when we relied on germanium before silicon completely took over. They wrote, quote, "While there may not be a silicon for superconductivity, this does not mean that we should not search for one, akin to searching for a small needle in a large haystack. Our current materials are okay, sure, but they are absolutely begging to be replaced by something better that we can actually scale up for industrial production." So to find that needle in a haystack, this roadmap lays out a strict 3-step programmatic pipeline. Step 1, heavily lean on computational modeling and machine learning to virtually predict new materials. Step 2, run thermodynamic screening to prioritize the most stable, viable candidates from those digital models. And then, only for the best of the best, Step 3, actual laboratory synthesis. The entire goal is to stop toiling blindly in a physical lab and minimize wasted time and resources. And when they finally do step into the lab, experimentalists have specific engineering knobs they can turn to tweak a material's properties. We're talking about physical manipulation, like exposing it to extreme pressure or strain. They can use chemical doping, which they can now test first inside computer simulations before ever making the physical material. They can even apply ultra-fast pulses of infrared light to briefly force a material into a superconducting state. It creates this beautifully continuous feedback loop between theoretical modeling and physical reality. Which leaves us with this final, thrilling question to ponder.
Will artificial intelligence and systematic computational modeling finally unlock the holy grail of room-temperature superconductivity? Honestly, we've moved so far past the days of just blindly mixing chemicals and hoping for a miracle. We are officially in the era of precision computational design. The laws of physics permit it, the roadmap has been drawn, now the scientific community just has to execute it. Thank you so much for joining me on this explainer today. The quest continues, and I for one cannot wait to see what they discover next.